Who did this? Let me be direct about what that question is implying and about why the honest answer is both more mundane and more scientifically interesting than the alien engineering scenario the phrasing is designed to evoke. No external agent turned off any star. No civilization, no weapon, no cosmic event that requires an actor. The specific phenomenon, this video, is pointing at the dramatic, documented, anomalous dimming of specific stars that has generated genuine scientific excitement and genuine scientific puzzlement over the past decade, has specific natural explanations that are fascinating precisely because they reveal how much we still don't understand about the specific internal physics of massive stars approaching the ends of their lives. But here is what is genuinely true in the headline. Astronomers have observed specific stars undergo specific dramatic Brintus drops that were not predicted, not fully explained at the time of observation, and in some cases still debated in the literature. The specific events are real. The specific scientific excitement is real. And the specific question of what physical processes are responsible, what is happening inside and around these specific massive stars to produce such specific dramatic dimming, is one of the most actively investigated questions in current stellar astrophysics. The star most people associate with this story is Betelgeuse, the specific red supergiant at the right shoulder of Orion, visible to the naked eye on winter nights in the northern hemisphere, one of the most luminous and most massive stars in the solar neighborhood. Its distance is approximately 700 light years, somewhat farther than the specific 500 claimed in the title, though Betelgeuse's distance estimates have themselves been the subject of significant recent revision. In late 2019 and continuing into early 2020, Betelgeuse underwent the most dramatic dimming event in the historical record of its observation. Its brightness dropped by approximately 35% over several months, reaching its lowest recorded visual magnitude before recovering. The specific event, called the Great Dimming, generated front-page coverage, genuine scientific debate, and a specific flurry of papers proposing competing explanations. And then there is VVVWIT08, a specific red giant star approximately 25,000 light-years away in the galactic bulge, observed by the VISTA variables in the Via Lactea survey, that underwent a specific dimming of approximately 97%, not 35% like Betelgeuse, but 97% over a period of approximately 200 days in 2012, before recovering to its previous brightness. A star that was, for approximately 200 days, reduced to 3% of its normal output, with no obvious explanation. And there is KIC 8462852, Tabby star, approximately 1,500 light-years from Earth, which underwent a specific series of irregular, aperiodic dimming events with specific, unusual properties that generated the most sustained public interest in a specific astronomical phenomenon since the discovery of fast radio bursts, including, briefly, serious scientific papers considering whether the dimming could indicate megastructures constructed by an advanced civilization. Who did this? The answer in every specific documented case is physics. Specific, interesting, not fully understood physics, but physics. Let me start with Betelgeuse's Great Dimming, because this is the specific event most directly associated with the headline, and because its specific resolution tells us something important about the specific internal processes of massive stars near the ends of their lives. Betelgeuse is extraordinary. It is a red supergiant, the specific class of massive stars that form when a star significantly more massive than the Sun, in Betelgeuse's case, approximately 16 to 20 solar masses, exhausts the hydrogen in its core and expands its outer envelope dramatically, cooling the the specific surface temperature from the specific tens of thousands of Kelvin of a main sequence massive star to the specific 3,000 to 4,000 Kelvin of a red supergiant. The specific expanded envelope extends outward to a radius of approximately 750 to 1,000 solar radii if placed at the center of our solar system. Betelgeuse would extend to approximately the orbit of Jupiter. The specific size of Betelgeuse creates specific observational opportunities available for no other star. It is the first star other than the Sun to have its specific disk resolved in direct imaging. The specific angular diameter of approximately 55 milliarc seconds, small though it is sufficient for the specific very large telescope, interferometer, and specific other high angular resolution facilities to produce specific direct images of the stellar surface, revealing the specific large convective cells, the specific photospheric brightness variations, the specific asymmetric surface structure that makes Betelgeuse one of the most directly characterized stars outside the solar system. The specific great dimming of 2019 to 2020 was therefore observed with extraordinary detail by an extraordinary collection of instruments: the Hubble Space Telescope, the VLT interferometer, the AAVSO network of variable star observers spanning decades, photometric monitoring programs across multiple wavelengths. The specific multi-wavelength, multi-facility monitoring campaign that the Great Dimming motivated produced the specific most comprehensive dataset ever assembled for a single stellar dimming event. The specific properties of the dimming were unusual. It was not uniform across the stellar disk. The southern hemisphere of Betelgeuse dimmed more than the northern, producing a specific asymmetric dimming pattern visible in the resolved stellar images. It occurred at a specific time when the specific long period pulsation of Betelgeuse, which oscillates with a specific period of approximately 420 days, was near its minimum, and it was accompanied by specific changes in the stellar spectrum that indicated specific changes in the temperature and density of the specific outer atmosphere. Let me take you to the specific resolution, or more precisely, the specific competing explanations that were proposed and the specific evidence that eventually favored one over the others. The specific first proposed explanation was the most dramatic. Betelgeuse, whose specific distance and specific mass make it a specific supernova candidate on astronomical timescales, it will explode as a core collapse supernova at some point in the next 100,000 years, was proposed to be showing specific precursor activity, specific changes in the specific internal structure, the specific neutrino emission, the specific convective dynamics that precede core collapse might produce specific external manifestations, including specific brightness changes that could be the specific observable warning of an imminent explosion. This explanation was never favored by the specific majority of the astrophysical community because the specific great dimming's properties didn't match the specific predicted signatures of pre-collapse activity. The specific timescale was wrong. Core collapse, when it occurs, happens on specific timescales of seconds rather than months. The specific spectral changes were not consistent with specific models of pre-collapse heating, and Betelgeuse recovered the specific brightness, returned to approximately its normal level by April 2020, which a specific star on the specific verge of core collapse would not do. The specific two explanations that divided the community were specific and distinct. The first, the specific cold spot explanation, proposed that the specific dimming was produced by a specific large convective cell on the stellar surface, cooler than the surrounding photosphere. Massive red supergiants like Betelgeuse have specific enormous convective cells, specific regions of hot, rising plasma comparable in size to entire solar radii that can produce specific surface brightness variations as they rise and fall. A specific, particularly large and particularly cool convective downflow could reduce the specific surface brightness in the specific affected region by the specific observed amount. The specific second explanation, the mass ejection explanation, proposed that Betelgeuse had ejected a specific large mass of material from its surface during a specific violent convective outburst, and that this specific ejected material had cooled and condensed into specific dust grains that then partially blocked the specific photospheric light reaching Earth. The specific dimming would be produced not by a specific intrinsic stellar brightness change, but by specific foreground dust absorption, the star appearing darker because specific material between us and the star was absorbing specific photons. The specific key discriminant between these two explanations was spectroscopic. A specific cold surface region would produce specific particular changes in the specific molecular absorption features of the stellar spectrum, specific cooler temperature signatures at the specific wavelengths affected. Specific dust absorption, by contrast, produces specific characteristic wavelength-dependent extinction, specific more absorption at shorter wavelengths than longer wavelengths, and specific absence of the specific temperature change spectral signatures. The specific Hubble Space Telescope observations of Betelgeuse during the Great Dimming, published in 2022 by Andrea Dupree and collaborators, provided the specific, most direct, and specific, most diagnostic data. The specific HST ultraviolet observations revealed that a specific large mass ejection occurred in 2019, a specific surface mass ejection similar to but vastly larger than the specific solar mass ejections we observe from our own Sunday. The specific ejected material expanded outward from the specific stellar surface, cooled and condensed into specific dust grains that produced the specific observed dimming. Simultaneously, the specific shock wave produced by the specific mass ejection disturbed the specific pulsation mechanism of the stellar envelope, temporarily suppressing the specific oscillation period and producing the specific cold surface region that the specific cold spot supporters had identified. The specific resolution was therefore not either or, but both. The specific great dimming was produced by a specific mass ejection that caused both specific surface cooling and specific dust formation. The specific first direct observation of a specific surface mass ejection event on a specific star. Other than the Sunday, let me now tell you about what the specific great dimming revealed about the specific internal physics of Betelgeuse, because this is the specific scientifically important conclusion that the specific dramatic headline obscures. Massive red supergiants like Betelgeuse were known before 2019 to be variable. They pulsate. They exhibit specific irregular brightness variations. They lose mass through specific stellar winds. But the specific great dimming revealed a specific mechanism for mass loss, the specific surface mass ejection that was not previously established observationally for red supergiants, and that may be significantly more important for the specific total mass loss of massive stars than the specific steady stellar wind models assumed. The specific mass ejected in the 2019 event was approximately 2 to 4 times the mass of the Moon, a specific large amount of material but small compared to the specific total mass of Betelgeuse. But if such specific ejection events occur regularly throughout the specific red supergiant phase, which lasts approximately 100,000 years for a star of Betelgeuse's mass, the specific cumulative mass loss from these specific episodic ejections could be comparable to or exceed the specific mass lost through the specific steady stellar wind. The specific consequence for the specific final fate of Betelgeuse is direct. The specific mass of the stellar core at the specific moment of core collapse determines whether the specific collapse produces a specific neutron star or a specific black hole, and whether the specific supernova explosion is energetic enough to be visible to the naked eye from Earth. The specific mass loss history of Betelgeuse throughout its specific red supergiant phase directly affects the specific core mass at collapse. Understanding the specific episodic mass loss mechanism which the specific great dimming revealed exists is therefore directly relevant to predicting the specific fate of the specific most carefully watched specific supernova candidate in the specific nearby universe. Let me now take you to VVVWIT08, the specific 97% dimming event that has generated less public attention than Betelgeuse, but that is in specific ways more scientifically puzzling. VVVWIT08 was discovered in data from the VISTA variables in the Via Lactea survey, a specific systematic infrared survey of the specific galactic bulge and southern disk designed to identify variable objects through repeated imaging over multiple years. The specific designation, WIT, stands for what is this? The specific nomenclature used by the specific survey team for specific objects whose specific behavior defies specific immediate classification. The specific dimming event occurred over approximately 200 days in 2012. The specific star, a specific large, cool giant, dropped from its specific normal brightness to approximately 3% of normal over approximately 100 days, remained at the specific minimum for approximately 30 days, and then recovered over approximately the same specific time scale. The specific light curve, the specific brightness as a function of time, has a specific flat bottom shape during the minimum that is characteristic of the specific foreground object blocking the specific stellar disk. The specific most likely explanation, favored by the specific discovery team led by Lee Smith at the University of Cambridge and published in the specific monthly notices of the Royal Astronomical Society in 2021, is a specific eclipsing companion, not a specific planet, which would be too small to produce a specific 97% dimming, not a specific other star, which would have specific observable spectral signatures. Specifically, a specific very large, very optically thick cloud of dust orbiting VVVWIT08 as part of a specific binary system, a specific companion object surrounded by a specific massive extended disk of opaque material that passed in front of the specific stellar disk as seen from Earth. This specific mechanism, sometimes called a specific disk eclipsing system, is the specific same mechanism proposed for Epsilon Aurigae, a specific famous long period eclipsing binary, approximately 2,000 light years from Earth, that undergoes a specific 2-year dimming event every 27 years, produced by a specific large opaque disk surrounding a specific companion star. VVVWIT08 appears to be a specific, more extreme version of this specific phenomenon, with the specific eclipsing object being a specific, more massive disk of more opaque material producing a specific, more complete specific occultation. The specific VVV survey has found several additional objects with similar specific dimming profiles, suggesting that specific large disk eclipsing systems are not unique rarities, but a specific class of astronomical objects that is more common than previously appreciated. The specific ongoing surveys of specific galactic variable objects by VVV, by OGLE, by VISTA, and other systematic photometric monitoring programs are accumulating specific larger samples of these specific systems that will allow specific statistical characterization of the specific dust disk properties and specific orbital distributions. Let me now take you to KIC 8462852 Tabby star, because this is the specific object that generated the most sustained public interest in specific anomalous stellar dimming and the specific most seriously discussed consideration of an artificial explanation. KIC 8462852 is a specific F-type main sequence star, hotter and more massive than the Sun, approximately 1.4 solar masses, located approximately 1,500 light years from Earth in the constellation Cygnus. It came to scientific attention in 2015 when Tabetha Boyajian and collaborators published a specific analysis of the specific Kepler Space Telescope data for this star, finding a specific unprecedented pattern of irregular aperiodic dimming events. The specific dimming events had specific properties that distinguished them from every previously cataloged class of stellar variability. They were not periodic. They did not occur at the specific regular intervals that would indicate a specific orbiting planet or a specific companion star. They had specific irregular shapes and specific irregular depths ranging from less than 1% to more than 20%, with no specific reproducible profile from one event to another. The specific deepest dimmings were too deep for any specific planetary transit. A planet large enough to produce a 20% dimming would be larger than the specific star itself. And the specific overall long-term brightness trend of the star showed a specific secular decline over the specific 4-year Kepler observation baseline. The specific, most dramatic proposed explanation came from Jason Wright and colleagues in a specific 2016 paper, the specific megastructure hypothesis. The specific argument was that the specific unusual properties of the specific KIC 8462852 dimming, the specific irregular depths, the specific aperiodic timing, the specific unusual shapes were consistent with what you might expect from a specific partial Dyson sphere or specific other large engineered structures in orbit around the star, blocking specific different fractions of the specific stellar disk at specific different times as specific different components of the structure passed in front. The specific paper was careful. It presented the megastructure hypothesis as one specific possibility among several, noted the specific principle that natural explanations should be exhausted before artificial ones are invoked, and emphasized that specific more data was needed to distinguish between specific competing explanations. But the specific public reception was less careful. The specific media coverage was overwhelming, and the specific public excitement about a potential specific alien megastructure around a specific nearby star was immediate and sustained. The specific subsequent investigation of KIC 8462852 carried out by Boyajian and a specific large international collaboration funded partly by a specific crowdfunding campaign produced the specific most comprehensive data set for this specific star since the specific Kepler observations. The specific key observational result was the specific wavelength dependence of the specific dimming. In a specific megastructure explanation, the specific dimming would be achromatic. The specific blocking object, being a specific rigid structure, would block specific all wavelengths of light equally. Specific more dimming at specific blue wavelengths than specific red wavelengths. The specific chromatic dimming characteristic of specific dust would specifically rule out a specific rigid structure and specifically require a specific material explanation. The specific Boyajian et al. Result, published in 2018, found specific chromatic dimming, more dimming at specific shorter wavelengths. The specific dipping events showed specific wavelength dependence consistent with specific dust particles of specific particular sizes, not with specific rigid structures. The specific natural explanation that emerged, and that is now the specific consensus among astronomers, involves a specific swarm of specific cometary bodies or specific dusty debris in specific highly eccentric orbits around the star. As specific different components of this specific swarm transit, the specific stellar disk, they produce specific different depths and specific different shapes of specific dimming events at specific different times, the specific irregularity being a specific consequence of the specific different orbits, specific different sizes, and specific different compositions of specific different members of the specific swarm. Who did this? No one. A specific natural debris field in specific eccentric orbits around a specific otherwise ordinary star, producing specific unusual photometric behavior that the specific unprecedented photometric precision of the specific Kepler telescope revealed for the specific first time. Let me now connect these specific three cases, Betelgeuse, VVVWIT08, Tabby star, to the specific broader scientific story they collectively tell. Each of these specific dimming events was, in its specific moment of discovery, genuinely puzzling. The specific properties of the specific dimming didn't fit the specific existing models. The specific Kepler photometry of Tabby's star showed specific dimmings that none of the specific standard stellar variability models predicted. The specific magnitude of Betelgeuse's specific great dimming was unprecedented in the specific historical record. The specific 97% dimming of VVVWIT08 was unlike anything previously cataloged by the specific VVV survey. In each specific case, the specific scientific community's response was exemplary, not jumping to specific exotic explanations, not dismissing the specific anomaly as specific measurement error, designing specific targeted observations to discriminate between specific competing explanations, accumulating specific additional data at specific multiple wavelengths with specific multiple instruments, publishing specific competing interpretations in specific peer-reviewed journals, and eventually converging on specific natural explanations that are more interesting scientifically, physically, astrophysically than any specific artificial alternative would have been. The specific natural explanations are more interesting because they reveal specific real, previously underappreciated physical processes. Surface mass ejections in red supergiants, a specific mass loss mechanism not previously established observationally. Disk eclipsing binary systems, a specific class of objects whose specific prevalence, the specific VVV survey, is revealing to be greater than previously appreciated. Cometary debris swarms in specific highly eccentric orbits, a specific revelation about the specific complexity of specific planetary system architectures around specific intermediate mass stars. Each specific anomalous dimming event has advanced our specific understanding of specific stellar and specific planetary physics in a specific way that a specific boring, unvarying star never could. Let me close this first part with something that directly addresses the who did this, framing not to dismiss the question, but to replace it with a better one. The specific appeal of the alien megastructure hypothesis for Tabby's star in particular was not irrational. The specific Kepler photometry showed something genuinely unprecedented. The specific, most reasonable interpretation of unprecedented is not natural, but unusually rare. It could be artificial, and therefore unprecedented in a specific universe where artificial megastructures have not previously been identified. The specific scientists who briefly entertained the megastructure hypothesis were not being credulous. They were following the specific logic of what genuinely unusual observations require. But the specific principle that natural explanations should be exhausted before artificial ones are invoked is not just a specific cultural bias. It is specific, statistically correct. The specific number of specific natural processes that can produce specific unusual light curves is vastly larger than the specific number of observed alien megastructures, which is currently 0. In the specific Bayesian calculation, the specific prior probability of a specific natural explanation, however, specific unusual is specific much higher than the specific prior probability of an artificial explanation. The specific investigation of Tabby star and of Betelgeuse's great dimming and VVVW-IT08 did exactly what specific good science should do. It took the specific anomaly seriously. It gathered specific more data. It tested specific competing hypotheses with specific observable predictions. And it converged on specific natural explanations that are genuinely interesting, genuinely informative, and genuinely advancing our understanding of specific real physical processes. Who did this? The specific internal convection of a massive red supergiant ejecting specific material from its surface. The specific orbital dynamics of a specific dusty disk around a specific binary companion. The specific chaotic gravitational evolution of a specific cometary swarm around a specific main sequence star. Physics. Specific, interesting, not entirely understood physics. In part 2, I want to go deeper into what the specific great dimming revealed about the specific internal dynamics of Betelgeuse's atmosphere that no previous observation had captured, into the specific newly discovered class of disk-eclipsing objects that VVVWIT08 exemplifies, and into something I find genuinely extraordinary: the specific connection between the anomalous dimming phenomenon and the specific broader question of what the specific onset of a specific stellar death actually looks like from the outside in real time as it is happening. Who did this? The specific universe in the specific most interesting and most informative ways it knows how. So we'd arrived at this place where the 3 most famous anomalous stellar dimming events of the past decade, Betelgeuse's great dimming of 2019 to 2020, VVVWIT08's 97% darkening in 2012, and Tabby star's irregular flickering across 4 years of Kepler data, each generated genuine scientific excitement, each briefly entertained exotic explanations, and each converged on natural explanations that turned out to be more scientifically interesting than any artificial alternative. Surface mass ejections, disk-eclipsing binary companions, cometary debris swarms, real physics, revealing previously uncharacterized phenomena in each case. Now I want to go deeper into what Betelgeuse specifically has been doing since the great dimming recovered, because the star has not been quiet, and the subsequent monitoring has revealed something extraordinary about the specific dynamics of its pulsation. into the growing catalog of disk eclipsing systems that VVVWIT08 represents, and what that population is telling us about planetary and stellar system architectures. And into something genuinely important, the specific observational signatures that would distinguish a star undergoing actual pre-supernova activity from the various transient dimming events we've been discussing. Let me start with what Betelgeuse has been doing since April 2020. The Great Dimming ended with a recovery to approximately normal brightness by April 2020, followed by a specific and remarkable development. Betelgeuse brightened to become significantly brighter than its historical average, reaching its highest observed visual brightness in decades by late 2020 before settling into a new pulsation cycle. The specific pulsation of Betelgeuse involves multiple overlapping periods. The dominant one, approximately 420 days, is driven by radial oscillations of the entire stellar envelope, the whole star breathing in and out. There is a second period of approximately 2,100 days, sometimes called the long secondary period, whose physical origin remains debated. And there are shorter periods of 180 to 200 days linked to higher order oscillation modes. The mass ejection event of 2019 disrupted this pulsation structure. The shock wave produced by the ejected material propagated through the stellar envelope, temporarily suppressing the oscillation. When the pulsation recovered, it resumed at essentially the same period but with a noticeable phase shift. The pulsation was reset, like striking a tuning fork to interrupt it and then letting it ring again from a new starting point. This phase reset has enabled something specific and scientifically valuable, a fresh, well-characterized baseline for monitoring the star's future behavior. Because the Great Dimming produced such a comprehensive multi-wavelength data set, and because Betelgeuse is now being monitored continuously by more instruments with better calibration than any previous epoch, any future mass ejection event will be caught in unprecedented detail. The monitoring matters because the mass ejection mechanism, now observationally established as real, has implications for the timeline of Betelgeuse's remaining life. The star is losing mass through this episodic mechanism at a rate that may substantially exceed the steady wind mass loss assumed in stellar evolution models. Higher mass loss rates mean faster evolution, potentially compressing the timescale to core collapse. The current best estimate for when Betelgeuse will explode as a core collapse supernova is within the next 100,000 years, a broad range that reflects genuine uncertainty in the stellar evolution models, particularly in how much mass the star will lose and how quickly between now and the final collapse. The mass ejection mechanism revealed by the Great Dimming suggests the current models may be underestimating that mass loss, which would shorten the timeline toward the lower end of the range. What does lower end mean practically? It means the supernova could conceivably occur within tens of thousands of years rather than hundreds of thousands. On human timescales, both are effectively infinite. But on stellar evolution timescales, the distinction between 10,000 years and 100,000 years is significant for modeling the pre-supernova evolution. Let me now take you to something about Betelgeuse that has received less attention than the Great Dimming, but that I think is equally important, the recent high-precision distance measurement that changed our understanding where the star is in its evolutionary cycle. For decades, Betelgeuse's distance was estimated at approximately 430 light-years based on the original Hipparcos satellite parallax measurement from the 1990s. This distance estimate was known to be uncertain. The star's enormous angular diameter and complex atmospheric structure make precise astrometric measurements difficult, but 430 light-years was the standard figure, used in all stellar evolution calculations. In 2021, a team led by Laszlo Molnar and collaborators published a new distance estimate based on specific pulsation analysis using the known relationship between pulsation period and luminosity for red supergiant stars to derive the distance. from the observed period and apparent brightness. The result? 530 to 570 light years, significantly farther than the Hipparcos estimate. A greater distance means a greater intrinsic luminosity for the same apparent brightness, and a greater intrinsic luminosity means a greater mass, approximately 16 to 19 solar masses, rather than the previously assumed 10 to 15 solar masses. This mass revision has direct consequences for Betelgeuse's evolutionary state and its expected fate. A more massive star burns faster, loses mass more quickly, and reaches the pre-collapse stage on a shorter timescale than a less massive star. The revised mass estimate is consistent with Betelgeuse being in a later and more evolved state than the earlier distance estimate implied, potentially in the core oxygen or neon burning phase rather than the earlier core carbon burning phase previously assumed. If Betelgeuse is burning oxygen or neon in its core, the timescale to core collapse is dramatically shorter than the timescale from core carbon burning. Carbon burning lasts approximately 1,000 years. Neon burning lasts approximately 1 year. Silicon burning, the final stage before collapse, lasts approximately 1 day. The uncertainty is still substantial. The current best estimates don't definitively place Betelgeuse in any specific burning phase, but the revised distance and mass estimates make it plausible that Betelgeuse is in a more advanced evolutionary state than previously thought, not necessarily about to explode on human timescales, but closer to that stage than earlier calculations suggested. This is why monitoring Betelgeuse is not purely academic curiosity. It is genuine scientific preparation for one of the most observable astronomical events possible in the foreseeable future, a naked-eye supernova from the nearest confirmed red supergiant candidate, close enough to be detected in neutrinos by underground detectors like Super Kamiokande and IceCube, and bright enough to be visible in daylight. Let me now take you to the growing population of disk eclipsing systems, the class of objects exemplified by VVV-WIT08, because this is where the story of anomalous stellar dimming connects most directly to the question of how planetary systems form and evolve around stars, very different from the Sunday. Disk eclipsing systems are binary stars or star plus substellar companion systems in which one member of the pair is surrounded by an extended disk of dust and gas that periodically transits the other member, as seen from Earth. The specific observable signature is a dimming event whose duration is determined by the orbital period and the disk geometry, whose depth is determined by how much of the stellar disk the disk occults, and whose shape reflects the specific density structure of the disk. The prototype for this class is Epsilon Aurigae, the brightest disk eclipsing system in the sky. Epsilon Aurigae is a supergiant star with a massive companion embedded in a large opaque disk. Every 27.1 years, the disk passes in front of the supergiant, producing a 2-year eclipse that dims the star by approximately 50%. The eclipse has been observed multiple times since the 19th century, and the most recent eclipse in 2009 to 2011 was monitored by an international campaign that produced the most detailed characterization of the system's disk structure yet achieved. VVV-WIT08 appears to be a more extreme version of this phenomenon, with a disk opaque enough to produce 97% dimming rather than Epsilon Aurigae's 50%. The flatness of the light curve, minimum the period during which the star maintained approximately 3% of its normal brightness for roughly 30 days, indicates that the occulting disk is substantially larger than the stellar disk, so that the stellar disk is completely covered for an extended period as the disk center passes in front. The Ogle photometric survey, the optical gravitational lensing experiment, which monitors hundreds of millions of stars in the galactic bulge and disk, has found additional candidates with similar light curve morphologies. A systematic analysis published in 2022 identified approximately a dozen objects with a specific flat-bottomed eclipsing profile that characterizes disk eclipsing systems, suggesting these events occur at a rate of perhaps a few per decade in the monitored fields. The disk eclipsing systems are scientifically interesting for several reasons. They are the most direct observational probes of disk structure around evolved or evolving stellar systems, the only astrophysical situations in which a large dust disk is revealed by its specific occultation of a bright background star. The timing, depth, duration, and chromatic properties of the eclipse constrain the disk size, opacity, vertical structure, and particle size distribution in ways that no other observational technique can approach. For VVVWIT08 specifically, the 200-day eclipse duration implies a disk with a very large physical extent comparable to or larger than the stellar disk being occulted, which is already a large red giant. This disk could be a protoplanetary disk around a low-mass companion, a debris disk around a stellar remnant, or the material associated with a mass-transferring binary system. Distinguishing between these possibilities requires spectroscopic observations of the specific system measuring radial velocity variations to determine the orbital dynamics that are challenging for an object 25,000 light-years away in the crowded galactic bulge. The next generation of large survey telescopes, Rubin Observatory's LSST, the Roman Space Telescope's wide-field imaging, will expand the known catalog of disk eclipsing systems enormously, enabling the population study needed to characterize the range of disk properties and orbital configurations that these systems represent. Let me now take you to the broader question of what anomalous stellar dimming can actually tell us about the final stages of stellar evolution and what the observable signatures of genuine pre-supernova activity actually look like. The question, what does a star look like just before it explodes, has a specific and somewhat surprising answer. For the most massive stars, stars above approximately 20 solar masses, the final years to decades before core collapse may be characterized by specific observable changes in the stellar atmosphere, driven by the increasing energy output of the deep interior as nuclear burning progresses through successively heavier elements. The specific mechanism is related to a phenomenon called super-Eddington luminosity in the stellar envelope. As the core energy generation rate increases in the final burning phases, silicon burning produces orders of magnitude more energy per unit time than carbon burning. The luminosity available to drive stellar winds increases beyond the specific Eddington limit, the threshold above which radiation pressure overwhelms gravity. Super-Eddington outflows can drive specific large-scale mass ejections events, similar to but more extreme than the mass ejection Betelgeuse experienced in 2019. This specific pre-supernova mass loss is observationally important because it creates a specific dense circumstellar medium, a shell of ejected material surrounding the star at the time of explosion. When the supernova shock wave subsequently expands into this material, the specific collision produces specific bright X-ray and radio emission and specific spectral features in the supernova light curve that encode information about the specific pre-supernova mass loss history. The specific connection to the dimming story is this. If Betelgeuse's 2019 mass ejection represents a genuine pre-supernova phenomenon, an enhancement of the episodic mass loss driven by increasing interior energy generation, then it may be the first directly observed example of exactly the kind of pre-supernova atmospheric activity that supernova models predict. Not an imminent supernova, as we established. The timescale to collapse remains uncertain and likely long. But potentially, the first observable sign of the specific evolutionary progression toward collapse that was previously understood only from stellar evolution models. The specific observational test is ongoing. If Betelgeuse's mass ejection events become more frequent, more energetic, and more coherent over the coming years and decades, if the pattern of events is consistent with increasing interior energy generation, driving increasingly powerful surface outflows, that would be observational evidence of the progressive approach to the final burning stages. If the ejection events remain irregular and broadly consistent with their previous historical behavior, the 2019 event was probably a normal stellar variability fluctuation rather than a pre-supernova signature. The monitoring continues with better instruments than any previous epoch, with a specific understanding of the mass ejection mechanism that the Great Dimming provided, and with the specific anticipation that whatever Betelgeuse does next, whether it eventually explodes or continues to vary for tens of thousands of years, will be observed in unprecedented detail. Let me now tell you about the specific class of objects that provides the best current observational constraints on what a star genuinely does in the final days to years before core collapse. Because these constraints come not from monitoring known candidates, but from studying supernovae that have already occurred and working backward. When a supernova is detected, the light curve, the specific brightness as a function of time after explosion, encodes information about the specific structure of the material surrounding the star at the time of explosion. Different supernova types show different specific signatures of the circumstellar medium that the progenitor star created through pre-explosion mass loss. The specific most informative class for pre-explosion activity is type IN. Supernovae whose spectra show specific narrow hydrogen emission lines produced by the specific interaction of the expanding supernova shock wave with dense pre-existing circumstellar hydrogen. The specific narrow lines indicate that the hydrogen was ejected before the explosion. The pre-explosion mass was moving slowly compared to the supernova ejecta, creating the specific spectral signature of slow-moving pre-ejected material being shocked by the fast-moving supernova blast. From the specific properties of the circumstellar interaction, the specific emission line profiles, the specific timing of the interaction signatures, the specific X-ray and radio emission produced, astronomers can reconstruct the specific mass ejection history of the progenitor star in the years to decades before explosion. The specific reconstruction tells you how much mass was ejected, how fast it was moving, and how long ago it was ejected. The specific results from studying the circumstellar media of type IN supernovae are revealing. Many of them show specific evidence for enhanced mass ejection in the years to decades before explosion. The specific dense circumstellar shells that the supernova shocks are interacting with were created by specific large mass ejection events in the pre-explosion epoch. And some type IN supernovae show evidence for specific, very recent mass ejection material ejected only months to a few years before the explosion, consistent with the specific final nuclear burning phases driving extreme mass loss immediately before collapse. This is the specific astrophysical context in which Betelgeuse's 2019 mass ejection is most interesting. Not because it was definitely a pre-supernova signature, the timescale evidence does not support that conclusion, but because it was directly observed evidence for the specific type of mass ejection event that in other stars has been found to be the pre-explosion signature. Knowing that this mechanism exists, knowing how it looks in real-time multi-wavelength photometry, and knowing how to distinguish it from normal stellar variability is direct preparation for recognizing it if it occurs in Betelgeuse or another nearby red supergiant in the future. Let me now tell you about something that connects the stellar dimming story to the search for life, a connection that is less obvious than the astrophysical stories we've been discussing, but that is genuine and important. The mass loss history of massive stars is directly relevant to the specific chemical enrichment history of the galaxy, which is directly relevant to the specific conditions under which planets form, which is directly relevant to the specific availability of the heavy elements that prebiotic chemistry and biology require. Massive stars are the primary factories for the heavy elements that make rocky planets and life possible. The specific elements, carbon, oxygen, silicon, iron, calcium, phosphorus, are synthesized in the specific nuclear burning phases of massive stars and dispersed into the interstellar medium by stellar winds and supernova explosions. The specific efficiency of this dispersal depends directly on the specific mass loss rates of massive stars across their evolutionary lifetimes. If the mass ejection mechanism revealed by Betelgeuse's great dimming is widespread, if red supergiants commonly undergo episodic surface mass ejections that the stellar wind models have underestimated, then the specific heavy element enrichment of the interstellar medium is more efficient than the current models assume. More efficient enrichment means faster chemical evolution of the galaxy, which means rocky planets with the right heavy element abundances have been forming for longer and in more locations than the current models predict. This specific connection, from Betelgeuse's great dimming to VVV-WIT-08's disk eclipse, to Tabby stars' debris swarmed to the chemical enrichment of the galaxy, to the prevalence of rocky planets, to the conditions for life, is not a loose metaphorical connection. Each step is physically traceable through the specific mechanisms we've been discussing. The dimming events reveal physical processes. The physical processes constrain the mass loss rates of massive stars. The mass loss rates determine the chemical enrichment of the interstellar medium. The chemical enrichment determines the composition of planetary building blocks. The composition of planetary building blocks constrains the prevalence of life-supporting worlds. Every time a massive star ejects material, every time it dims, like Betelgeuse dimmed in 2019, it is contributing to the specific chemical inventory that makes planets and eventually life possible. The specific mass ejection event that produced the Great Dimming dispersed approximately 2 to 4 lunar masses of material, including specific enriched elements from the outer stellar envelope into the surrounding interstellar medium. That material will eventually be incorporated into the molecular clouds from which future stellar systems form. The star that turned off, however briefly, however partially, was in the process of giving itself away. Let me close this second part with something that honestly captures the scientific significance of the anomalous dimming phenomenon as a whole. The specific pattern that emerges across Betelgeuse, VVV-WIT-08 and Tabby star, is revealing. In each case, the specific anomalous behavior was discovered by a specific instrument doing something other than looking for that specific phenomenon. Betelgeuse's dimming was noticed by the Standard Variable Star Monitoring Network that has been tracking its brightness for a century. VVV-WIT-08 was found in a survey designed to look for gravitational microlensing events toward the galactic bulge. Tabby star was identified through crowdsourced analysis of Kepler data by citizen scientists looking for planetary transits. None of these programs was designed to find the specific phenomena that were ultimately discovered. Each found something unexpected, something outside the specific category of objects the survey was built to catalog, because the photometric precision and the temporal sampling and the sky coverage happened to be sufficient to detect it. This is a specific and important lesson about how astronomical discovery actually works at the frontier. The most important discoveries are often not found by programs designed to find them. They are found serendipitously by programs designed for other purposes, operating at sensitivities high enough to capture unexpected behavior. The Vera Rubin Observatory, which we've discussed throughout this series in the context of Planet 9, near-Earth asteroids, transient events, and large-scale structure, will monitor approximately 37 billion astronomical sources in the sky repeatedly over a 10-year baseline. Its specific photometric precision and specific temporal cadence will be sufficient to detect dimming events like Betelgeuse's great dimming for millions of stars across the galaxy. Its specific wide-field coverage will reveal populations of disk-eclipsing systems, anomalous stellar variables, and unexpected transient phenomena at scales that no previous survey has approached. The specific next decade of astronomical discovery in stellar variability, what the LSST will reveal about how stars actually behave over years and decades of continuous monitoring, is the scientific frontier that the Betelgeuse, VVV, WIT-08, and Tabby star stories are the specific opening chapters of. In part 3, I want to bring everything together into the complete picture of what the anomalous stellar dimming phenomenon means for how we understand the final stages of stellar evolution, for what we should look for as genuine precursors to the next nearby supernova, and for what I think is the most profound implication of the entire story, not who turned off a star. What it means that we are now, for the first time in history, building instruments sensitive enough and surveys comprehensive enough to watch specific stars change, to observe the specific drama of stellar evolution in real time, rather than inferring it from the frozen snapshots of individual objects. Who did this? The stars themselves, doing what massive stars do at the ends of their lives, shedding their outer layers, contracting their cores, building toward the specific cataclysmic endpoint that will scatter their hard-won heavy elements across the galaxy. And we are watching, for the first time, in enough detail to actually understand what we're seeing. So we'd arrived at this place where the anomalous stellar dimming events, Betelgeuse's great dimming, VVVWIT-08's 97% occultation, Tabby stars' irregular flickering represent not alien engineering, but specific, natural, physically revealing phenomena, where the great dimming established surface mass ejections as a real mechanism for red supergiant mass loss with direct implications for stellar evolution models and heavy element enrichment, where the revised distance and mass estimates for Betelgeuse suggest it may be in a more advanced evolutionary state than previously assumed, and where the growing catalog of disk-eclipsing systems is revealing a previously undercharacterized class of stellar system architecture that wide-field photometric surveys are only beginning to map comprehensively. Now I want to bring it all the way home into what the anomalous dimming phenomenon means for how we understand stellar death in real time, into what genuine pre-supernova signatures would actually look like and how we would distinguish them from normal variability, and into what I think is the most important and most personally significant implication of the entire story, what it means to be living in the specific generation that first developed the instruments to watch stars change in real time with enough detail to understand what the changes mean. Let me start with the most important observational question. If Betelgeuse were genuinely approaching core collapse on a timescale of years to decades rather than the more likely tens of thousands of years, what would we expect to see? The specific answer requires understanding the specific timeline of the final nuclear burning stages. After core carbon burning, which lasts approximately 1,000 years for a star of Betelgeuse's mass, the core contracts and heats until neon burning begins, lasting approximately 1 year. Then oxygen burning, lasting approximately 6 months. Then silicon burning, lasting approximately 1 day. Then the specific core, now composed primarily of iron, can no longer release energy through fusion. Iron is the specific end product of nuclear burning, beyond which no energy is available from further fusion, and the specific core collapses on a time scale of seconds. The specific observable precursors to this sequence are several. During the final years to decades of carbon burning and through the neon and oxygen burning phases, the stellar luminosity increases, the core energy generation rate grows, and the energy is eventually deposited in the envelope, driving stronger stellar winds and potentially more energetic mass ejection events. The pulsation period may change as the stellar structure adjusts to the increasing core energy generation. The envelope dynamics change in specific ways that affect the oscillation modes. During the silicon burning phase, the final day before collapse, the specific neutrino emission from the core increases dramatically. Silicon burning in the core produces specific large numbers of neutrinos through specific weak interaction processes. These neutrinos escape the stellar interior essentially unimpeded, carrying away specific energy that the envelope does not receive. This neutrino cooling makes the final day before collapse different from all preceding stages in a specific, potentially observable way. Underground neutrino detectors, Super Kamiokande in Japan, IceCube at the South Pole, SNO+ in Canada, and others are specifically sensitive to the neutrino flux that would be produced by a core collapse supernova within several kiloparsecs of Earth. For Betelgeuse, at approximately 550 light years, the specific neutrino burst at the moment of core collapse would produce an estimated several thousand detectable neutrino interactions in Super Kamiokande alone, a spectacular signal impossible to confuse with background. But even before core collapse, the enhanced neutrino emission of the final burning stages may be detectable. A specific 2021 paper by Patton, Lunardini, Farmer, and Timms calculated that Super Kamiokande, combined with the specific Juno detector currently under construction in China, could detect the enhanced pre-collapse neutrino flux from Betelgeuse during the silicon burning phase, providing approximately 24 hours of warning before the visible supernova brightening reaches Earth. 24 hours of warning that Betelgeuse is about to explode. Not enough warning to do anything practically different on Earth, but enough warning to alert the astronomical community to prepare the most comprehensive multi-wavelength monitoring campaign in the history of astronomy, catching the supernova shock breakout, the specific rising luminosity, the specific gamma ray burst, if any, the specific neutrino burst, the specific gravitational wave signal, if detectable. Let me now tell you about what a Betelgeuse supernova would actually look like, because this is the specific astrophysical event that the entire monitoring program is ultimately preparing for. And its specific properties would make it the most observable astronomical event in approximately 400 years. The last supernova visible to the naked eye was SN 1987A, an event in the Large Magellanic Cloud, approximately 170,000 light years from Earth, that reached a peak apparent magnitude of approximately 2.9. Bright enough to see without a telescope, too faint to be seen in daylight. Betelgeuse is approximately 300 times closer than SN 1987A. The specific apparent brightness of a supernova scales as the inverse square of distance closer by a factor of 300 means brighter by a factor of 90,000. A Betelgeuse supernova would peak at an apparent magnitude of approximately -12 to -14, comparable to the full moon, possibly brighter. This is not a subtle event. A Betelgeuse supernova at peak brightness would be visible in broad daylight. It would cast shadows at night. It would be detectable by the naked eye as a specific point of light at the position of Betelgeuse, currently the right shoulder of Orion, shining with the brilliance of the full moon from a star-sized source. The specific duration would be weeks to months at or near peak brightness, followed by a specific slow decline over months to years as the supernova ejecta expands and cools. The specific remnant, a specific expanding shell of gas, and a specific central neutron star or black hole would be a specific bright radio and X-ray source visible for centuries with telescopes. The specific scientific value of such an event would be extraordinary. The specific nearby distance close enough to resolve the expanding shell in the first hours after the explosion would provide the most detailed observational test of core collapse supernova models ever achieved. The specific neutrino burst detectable in underground detectors worldwide would provide the most precise measurement of the specific neutrino properties and the specific core collapse dynamics. The specific gravitational wave signal potentially detectable by LIGO and Virgo for a galactic or near-galactic supernova would provide the first specific direct measurement of the gravitational wave emission from core collapse. A Betelgeuse supernova would be, in a specific and unambiguous sense, the most scientifically valuable single astronomical event of the modern era, surpassing even the specific GW 170817 neutron star merger detection in the specific breadth and depth of the information it would provide. And we are specifically prepared for it in a way that no previous generation was, with specific neutrino detectors that will give specific advance warning, with specific gravitational wave observatories that will detect the core collapse signal, with specific optical, infrared, ultraviolet, X-ray, and radio telescopes, automated, network, calibrated, ready to observe within seconds of notification. The Great Dimming of 2019 was, among other things, a specific dress rehearsal, a specific test of the specific global monitoring network, a specific demonstration of what the multi-wavelength, multi-facility response to a dramatic stellar event looks like in practice. The specific lessons learned in coordination, in calibration, in the specific rapid publication of specific multi-wavelength data sets will make the response to the actual supernova better than any previous generation could have mounted. Let me now address the specific personal dimension of what it means to monitor a specific star whose death we can anticipate but not predict with precision. Betelgeuse has been part of human consciousness for as long as humans have looked at the night sky. The specific red star at the shoulder of Orion was named by Arab astronomers Betelgeuse, derives from the Arabic for the armpit of the central one. It is visible from every inhabited location on Earth except the extreme southern polar regions. It has been a specific reference point for navigation, for storytelling, for the specific human experience of the night sky for thousands of years. We now know something about Betelgeuse that no previous generation knew. We know it is dying, not metaphorically, literally. The specific nuclear fuel that has sustained it for approximately 10 million years is nearing exhaustion. The specific iron core that will eventually accumulate to the specific Chandrasekhar mass and trigger collapse is building layer by layer through each successive burning phase. The specific supernova that will dissolve the specific familiar asterism of Orion, removing the specific red star from the winter sky, is coming. We don't know when. The uncertainty is genuine and currently irreducible. The specific evolutionary state of Betelgeuse is not determined precisely enough to distinguish between the timescales of thousands and hundreds of thousands of years that the different models imply. But we know it will happen. We know approximately what it will look like. And we are, for the first time in the entire history of human observation of the night sky, building the specific instruments that might detect the specific neutrino precursor signal before the specific visible explosion arrives. This specific knowledge, partial, uncertain, but real and grounded in specific physics, changes the relationship between the observer and the observed in a way that deserves acknowledgement. We are not simply watching a star. We are watching a star die with enough understanding of the process to prepare for it, to plan for it, to design specific instruments that will extract maximum scientific information from the specific event when it occurs. This is a specific form of anticipation that has no precise analog in the history of astronomy. Individual eclipses and planetary conjunctions have been predicted for centuries. But the specific anticipation of a nearby supernova, uncertain in timing but certain in occurrence, prepared for with specific neutrino detectors and specific gravitational wave observatories and specific automated optical alert systems, is something genuinely new. Let me now connect the stellar dimming story to the broader arc of what this entire series has been building. Throughout these conversations, from the gravitational wave background to the black hole information paradox to the cosmic web to the cosmological constant problem, we have been finding the same pattern. The universe reveals its secrets not all at once, not in dramatic single discoveries, but in the specific accumulation of observations that each advance understanding by a specific incremental amount. Each anomaly resolved, each model refined, each new instrument revealing the next generation of puzzles. The stellar dimming story is this pattern at its most personal and most immediate. Not the early universe, not distant black holes, stars visible to the naked eye, stars with names. Stars that human beings have looked at for thousands of years and told stories about. And now, for the first time, watching those stars change. Not just cataloging their static properties, observing their dynamics, catching a specific mass ejection in real time. Watching the recovery of a pulsation cycle, measuring the chromatic signature of a specific dust occultation, following the specific light curve of a specific eclipse by a specific disk around a specific binary companion 25,000 light years away. This is the specific new capability that the current generation of photometric monitoring programs has enabled. Not just classification, dynamic observation. The specific ability to watch a star do something specific and ask, what does this tell us about the specific physics happening inside and around this object? Betelgeuse's great dimming told us about surface mass ejections. VVV WIT08's eclipse told us about the population of disk eclipsing binary systems. Tabby star told us about the complexity of cometary debris architectures around intermediate mass stars. Each specific anomaly, investigated with specific instruments and specific techniques, revealed a specific physical reality that stellar astrophysics had not previously characterized observationally. The Vera Rubin Observatory will find thousands more. Not all of them will generate the same public excitement as Betelgeuse or Tabby star. Many will be discovered, investigated, classified, and understood without generating any headlines at all. The specific normal scientific process of accumulating knowledge about the specific diverse phenomena of the stellar universe. But some will be extraordinary. Some will be the specific first detection of a specific phenomenon not yet imagined. Some will be the specific first real-time observation of a specific physical process that stellar evolution models have predicted but never before directly seen. And one, eventually, will be the specific neutrino precursor signal from Betelgeuse or from some other nearby massive star that no one is currently watching, especially carefully giving the specific 2-4 hour warning that a specific supernova is about to occur in our specific cosmic neighborhood. Let me close with the most important and most personally significant thing that the stellar dimming story tells us, not about the specific physics of red supergiants or disk eclipsing binaries or cometary swarms, but about what it means to be the specific generation that developed the capacity to watch stars change, For the entire history of human astronomy, from Hipparchus cataloging stellar brightnesses in the 2nd century BCE through Galileo turning his telescope on the Jovian moons, through Hubble measuring Cepheid distances to galaxies, the fundamental operation of astronomy was classification, measuring the properties of astronomical objects at a specific moment in time and inferring from those static properties the physical nature of the objects. This is still most of what astronomy does. But the specific new capability, the specific ability to monitor specific objects continuously over years and decades with specific photometric precision sufficient to detect specific sub-percent brightness changes, is transforming a specific subset of astronomy from classification into something more like biology, not measuring a specific organism's morphology at a specific moment. Watching it live, watching Betelgeuse's atmosphere convect, watching a specific mass ejection erupt from the specific stellar surface, watching the specific pulsation recover from the specific disruption of the specific ejection event, watching the specific long-term evolution of the specific star's brightness and temperature and mass as it approaches its specific end. Who did this? The universe, doing what it does, evolving, changing, processing the specific nuclear fuel of its stars, building the specific heavy elements that will eventually be scattered into the specific interstellar medium that will eventually become the specific molecular clouds that will eventually form the specific next generation of stars and planets. And we did this, built the specific instruments, designed the specific surveys, analyzed the specific data, and understood the specific physics well enough to watch it happening. This specific dual achievement, the universe doing extraordinary things, and we understanding what we're watching, is the specific thing that makes the stellar dimming story not just scientifically interesting, but personally significant. Every specific night that the specific monitoring networks are watching specific stars, every specific photometric data point being added to specific light curves of specific millions of specific objects across the specific galaxy is a specific act of attention, of the specific kind of sustained, patient, careful attention that reveals specific physics that snapshot observation cannot. The specific stars are doing specific things. They have always been doing specific things. But we are now, for the first time in the history of our species, paying specific enough attention to see what those things are. That specific attention, sustained over specific years by specific scientists with specific instruments on specific mountains under specific dark skies, is what found the specific great dimming and the specific 97% eclipse and the specific irregular flickering of Tabby's star. And it is what will find the specific next anomaly. And the one after that, and eventually at a specific moment that no current model can predict precisely, the specific neutrino signal that announces the specific death of a specific star that human beings have watched for thousands of years. Who did this? The stars, following the specific physical laws that govern them from the specific moment of their formation to the specific moment of their death. And us finally watching carefully enough to see that is the specific answer. That is the specific extraordinary thing about this specific moment in the history of astronomy. The stars are dying. We are watching. And for the first time, we understand enough of what we are watching to know what it means